Unit 9.8. So we're going to relate what we just did last time with E-cell, and a little bit earlier in Unit 9, free Gibbs energy, and see where that takes us. So that's actually two sections here, 9.8 and 9.9. But we'll also talk about what happens if you're not at standard conditions. The AP folks used to have students calculate what would happen at non-standard conditions, but at this point we're just theoretically going to talk about what happens at non-standard conditions. So remember, non-standard conditions are 25 degrees Celsius and one atmosphere if it's a gas, but 1 molar if it's a molarity, which typically we would be dealing with molarities, not with pressures. So to be able to reconcile units, there is a relationship between energy, joules, and our energy that we've been dealing with in electrochemistry. And introducing a new, well, actually we've talked about Coulomb's law, but we also have the unit Coulomb, which it deals with the charge. And we're going to be using this frequently, Faraday's constant, and that's in your equation sheet. And some books have it as 96,500. Your equation sheet for the AP folks is 96,485. There's times where I might go back and forth between 96,500 and 96,485. But if I'm taking the test in May, which I guess I'm not, but if I was, I would be using 96,485 because that's what's provided for me on the test. And then we also have an equation that deals with free Gibbs energy, but it also deals with E-cell. So N is important, and we'll have to be able to identify how many moles of electrons are being transferred in the chemical reaction. And then we'll have to solve for E-cell generally to be able to solve for free Gibbs energy. And you know from previous units that if you have that, that means thermodynamically favored. That means more left to right than right to left. And also from previous sections, we know that E-cell positive means that's thermodynamically favored, and the reaction runs left to right, not right to left. And so that's what this says down here at the bottom. So let's jump into a question. So before we go too far, if you were going to take these two half reactions, well, get those two half reactions and join them together to make a full reaction, you need to multiply this half reaction by 2, and you need to multiply this half reaction by 3 to be able to get that to show up in a balanced chemical equation with no electrons. Because remember that whatever electrons you lose, something else has to gain. So there are 6 electrons that are transferred in this chemical reaction. And then to be able to understand the rest of it, I guess we need this equation, negative N F E. Remember that N is moles of electrons, F is Faraday's constant, a constant, and then E-cell is whatever E-cell. So it looks like we're going to have to use those to get the E-cell. So gold to gold ions is oxidation. So this is the oxidation half reaction voltage. And then calcium ions to calcium metal is the reduction half reaction. So that means we have to put this one first and the second one second. Well, the 1.40 volts second, I should say. So we have negative 2.87 minus 1.40. Okay. And that's going to give us a very negative value. So that means that this reaction is not thermodynamically favored. So we already know that delta G should end up being a positive, and it will, because the negative that's in 4.27 and the negative that's in negative NFE, they're going to cancel out. We will get a positive there. At this point, I think it's just plug and chug. The hardest part is knowing that there's 6 electrons and that you had to solve for E cell. 96,485. And the units, let's go back, revisit these units. Coulombs per mole electron. But remember that coulombs times volts will give you joules. Whoops. So what that means is that the coulombs that we just mentioned in the 96,485 and the negative 4.27 volts will combine to make these joules. So our unit, or units, will be joules per mole. Now, it's going to give you a gigantic number, so most people are going to divide that by 1,000 to get into a kilojoules number, which I think I'm going to also do here because I don't want to write out all those zeros or times 10 part of it there. So there's the answer, and it is a positive. So again, shows that it's not thermodynamically favored. Takes energy to make that reaction occur. Under standard state conditions, what's spontaneous, meaning what thermodynamically favored reaction will occur if you have this combination. So I gave you lots of half reactions, but we're not using all of them. Tin 4 to tin 2, so we need that. And iron 3, iron 2, we need that. And then we're looking for an E cell that is positive. So how can we rearrange those to get a positive answer? And I think the only way you can do that is like that. So the standard E cell would be 0.62, and since we put the 0.77 first, that's the reduction half reaction, and then that would have to be the oxidation half reaction. So let's write that out. Iron plus 3 goes to iron plus 2. And by the way, we'd have to multiply that by 2 because we need 2 electrons to cancel with 2 electrons. And then this is the oxidation. That means that right now it's written as reduction. We'd have to switch that around. And there we go. It didn't ask us to do anything else, but if we wanted to solve for delta G, we'd have to just plug and chug, but we'd have to know that 2 electrons would have to go in for N. Okay, so if we wanted, your textbook has this in it, so I thought it might be nice to include this. But if you had wanted to solve for what happens at non-standard conditions, so here are our standard conditions, but then sometimes we have non-standard conditions. And to go from standard to non-standard, we have to revisit the reaction quotient. And so the reaction quotient generically looks like this, but you may not have all those spots because remember, if it doesn't have molarity, it doesn't belong in the reaction quotient. So there are a couple other aspects here. But you can talk about, will the voltage go up or go down? So like if maybe the standard voltage was 1.10 volts. Well, someone says to you, hey, is there any way we can up this voltage and get it to, I don't know, let's say we want it to be 2.5 volts. Is there any way to get that normal conditions 1.10 volts to a 2.50 volts? And yes, we could. And so the idea would be, if you, let's just say these are all molarities to keep these all like that. If you would up the ante, up the molarities of those two items, decrease the molarities of those two items, or any combination of that, maybe you're not manipulating all four of those things at once, you could get the voltage to increase. Okay, and how would you be able to figure that out? I guess you'd have to put 1.10 volts here. You'd put 2.50 volts there. We don't know what the reaction is. Let's just say there's 2 moles of electrons transferred there. I'm just making up an equation now. And then you could solve for this ratio of reactants and products, actually products up top, reactants on the bottom. And when you solve for that ratio, you can manipulate that ratio to get whatever you wanted to happen. Okay, but that, you might have a couple of questions for homework, but that, the Nernst equation will not be on your test. But I put that there because when you take college chemistry, there's a very good chance you will have some math with the Nernst equation. We will talk, and we've talked previously about Q versus K, and this is just revisiting this again, but in terms of electrochemistry, if Q increases, cell voltage will decrease. It's more like, so if Q goes up, it shifts more to the left, and this is nothing new. If Q decreases, Q is smaller, then it shifts to the right. And so left and right, we can talk in terms of voltage this time. That's all. This one up here is kind of boring. This is where it is in actually the dynamic equilibrium, and forward and reverse reactions are happening at the same speed. You would see this as your maybe you have you have batteries in a flashlight. The flashlight would be so dim it's you would go, oh, my batteries are dead. So we've actually already touched upon Le Chatelier's principle. So this is nothing new. This isn't a true in the same context that we've talked about in the past with equilibrium, but we can use very much equilibrium aspects to this for sure. So if you would increase something over here, it's going to shift it to the left to right. And it's all in terms of Q versus K, which we just visited a couple seconds ago. If you would decrease the reactants, it's going to shift it more towards the reactants. And I could keep going with that idea there. But it's all about the Q versus K. Okay. This is where we can't talk about Q versus K. But if you would have your car outside in the middle of wintertime and the battery is very, very cold, and you try to turn your car on, you start your car, it will have a decrease in voltage, and it might be to the point where your car won't start. I don't recommend trying this, but if your temperature of your battery would increase, very dangerous to do this, so I'm not recommending that at all, but you might be able to increase your voltage. Problems with batteries is that how they're stored, how the chemicals are situated in there. It's dangerous to increase the temperature of your battery. This is interesting point here. As soon as the reaction starts, the reactant molarities will go down in concentration, and the product molarities will go up in concentration. So just by having the reaction proceed, the voltage will actually proceed, will get lower and lower and lower. So if it started at 1.10 volts, after a period of time, it will be lower than 1.10 volts. You may not be able to see this happen. It depends on what that voltage is and how things are set up in your battery, but you possibly could. Nernst equation questions. Write the net ionic. So remember, this is line notation. Magnesium becomes magnesium ions. And nickel ions become nickel metal. So there we go. There's our balanced net ionic reaction. Calculate E cell. Well, to calculate E cell, we got to go find the half reaction that deals with magnesium and magnesium plus 2 ions, and we have to find the half reaction that deals with nickel metal and nickel plus 2 ions. And so you need the back of the book, or actually I think it's not in the back of the book, it's actually embedded in the chapter. And so when I found those two values, the magnesium value was negative 2. I'll just write it over here. Negative 2.37 volts, and the nickel was negative 0.26 volts. So the only way you're going to get this to work is by placing the negative 2.6 first, and the negative 2.37 second. Okay. Observations. So you would be able to see the magnesium metal decrease in mass. You would see the nickel increase in mass. You'd probably have to put this on a balance before you started and after at a period of time. And then the other thing you could see is nickel ions are green. So over a period of time, that green color would start to fade and fade and fade and fade. If you wanted to increase or decrease the voltage, what could you do? Well, just on its own, the nickel ions will, over a period of time, they'll decrease in molarity, and the magnesium ions will increase in molarity, and the voltage will go down. So that would be two items for the voltage to be decreased. You could also make this reaction colder, and that would work also. The magnesium and nickel metals are not going to impact the voltages because they're not in the Nernst equation, they're not in the Q expression. And then for increases, it would just be the opposite ideas. So you could do those two things. So instead of using 1 molar nickel ions, 2 molar nickel ions. Instead of using 1 molar magnesium plus 2, maybe you're using 0.5 molar. So those would work. Questions. 45. What's the standard cell potential for the galvanic cell Z? Well, it looks like we don't know. So how are we going to figure that out? Well, it's sort of a Hess's law system of equations kind of idea. We do know these two things. And with those two things, we can get the third. So there's iron. There's iron. There's copper. There's copper. And the rest of things will fall into place. A couple things will cross out. All the aluminum items will cancel. And did you notice that the copper's in the right spot, but the iron is not in the right spot? So just like in Hess's law. We got an answer there. Okay, we're good to go with 45. 46. What's going on with Y and Z? Which of the following takes place in the half cell 3? Well, that's the iron. It says up here. So what's going on with iron? Let me erase all the stuff I had going on there because we have another question now. Well, iron ions going to iron metal. That is, for iron, that's being reduced. And then iron metal going to iron ions, that's being oxidized. So I guess that would have to be C. 47. Okay, now we're replacing 1 molar with 5 molar. What would happen? So let's erase all that again. So where do we have iron metal? Whoops, not iron metal, iron ions. Okay, so in Y, we're increasing the reactant. In Z, we're increasing the product. So this one, the voltage should go up, and this one, the voltage should go down. And there we go. Okay, here's our galvanic cell. We have lots of things we like. If this was a test question, I would prefer if you guys would label the anode, cathode, show, whoops, I don't really want to put 2 electrons. I don't know why I did that. I think in this one it's going to be 3 electrons. The arrow of which way these electrons are traveling. Also the arrows of how the ions are traveling. And then, oh, there's no salt bridge in this either. So we'd have to put a salt bridge in there. Part A, the student measures the voltage and it's a 0. Identify the missing component. Well, I think we just did that. It's missing the salt bridge. B, calculate the E cell for the half reaction chromium. Well, we've always solved for E cell. Well, this time we're not because we have E cell. So 1.54 equals reduction minus oxidation. So 1.54 equals, now we have to figure out where are we going to put all these numbers. So I think we're going to have to put it in this spot. And I think if we do that, we're going to get negative 0.74 volts. Okay. Let's just make sure we need something else here. Okay, so it already tells us the silver ions are reduced. So that's why we put that one in that spot. I guess I should have said that initially when I put the 0.8 in there. Okay, so part 2, right, balanced not ionic. So we need silver ions. You know what, I'm not going to have a lot of room there. Let's put it over here. Silver ions going to silver metal. And that means that this has to be oxidized. So, you know what, I didn't give myself enough room at all there. Chromium plus silver ions going to silver metal and chromium ions. And then that's not going to balance. We'd have to put a 3 there and a 3 there. Calculate delta G. Oh, it wants it in joules per mole. So we have negative N Fe. So how many moles of electrons are transferred? We have 3. 96,485 coulombs per mole of electrons. And voltage, we just were given 1.54 volts. Multiply those together. I think we have answers, so maybe we'll just go down and look at the answers. And it's going to be a gigantic value, because typically people don't leave these in joules, but it wants it in joules this time, and it will be a negative because we have that negative outside there, and so that is thermodynamically favored. Okay, so I guess we handled all those questions. We have our last questions here. We're doing a titration, and here are a couple possibilities of titrations. We got a bunch of E cells for half reactions. Use the information in the table to calculate the following. E cell for the reaction between dichromate and hydrogen peroxide. Okay. So we need hydrogen peroxide as a reactant, and we need dichromate as a reactant. So it looks like there's both in there as reactants, but remember that these are all written as half reactions, reduction half reactions. You always need something to be oxidized and something to be reduced. So that would work. So I think that would be 1.33 minus a 0.70. So you can't forget that you need something to lose electrons, you need something to gain electrons. You can't have reduction reactions. Cobalt and hydrogen peroxide. Cobalt ions, I should say. So it's already written there as a product. So I think in that case we need to use those two. Let's move that up just a little bit here. 1.77 minus 1.84. Oh, that's going to give you a negative value. So that means if you're trying to do titrations, that's going to happen, and that's not going to happen. I think we just actually inadvertently answered that question there. So we're going to have to use dichromate. We can't use cobalt ions. And then calculate delta G for the reaction you chose. So we're going to have to use that voltage and that equation. So how many electrons are transferred between the between these two reactions? Well, 6 won't cancel with 6. So I think we had to multiply that entire reaction by 3. So 6 electrons. Faraday's constant, 96,485. And then E cell was 0.63. And we probably have some answers down here. And there we go. So this time they actually did convert it, because it asked for kilojoules per mole. So we had to divide that by 1,000 to get it into the kilojoules per mole. And there we go. I think that's it.